in some problems with anti-differentiation, it's quite difficult to just anti-differ just by not recognition, but by just looking at it. So sometimes you actually want to help yourself out by differentiating something that you do know. So let's say you differentiate a function and you can find a derivative through some sort of means that you know, and you can take the fact that once you know the derivative, if you anti-diff this, you can get back what you differentiated in the first place. And so it sounds a little bit confusing at first, or something you take for granted even, that this process here is reversible. So this and this, they're reversible. But it does really help with some of the more complicated ones. So let's look at this one down here. Now, we know how to differentiate this one in the first place, this function of f. Sorry, not function f, the function f of x. So first of all, let's find the derivative and let's see how we can anti-diff something that's a little bit harder, and that's the function down here, or not function, this expression and the integral of it. So if you want to take the derivative here, you want to use the chain rule. So remember that the chain rule is dy dx is equal to dy du multiplied by du dx. So you can use this, or of course, imagine what kind of substitution you're using. So in this case, you know that what's inside the bracket is u. So when we find f dash, we're going to say that we're going to take the derivative of u to the power of 6 with respect to u. So I'm going to get 6, everything in the bracket, it's 4x, and it's now u to the power of 5. But of course, if we use the chain rule over here, we must finish off by multiplying by the derivative of our substitution with respect to x. So we're taking derivative of the cubic inside the bracket. So 2x cubed turns into 6x squared, minus 5x squared turns into minus 10x, minus 4x turns into minus 4. Okay, so from here, that can be your final answer if you don't want to factorize any further. But let's just have a look at what we can change to this expression over here before we try to do part B. Now we can see over here there's some similarities and some things that are a little bit different. So first of all, you can see that these three terms here are the same in both, as well as the index here of 5. These are the same. But what's not the same is this second bracket over here and the second bracket in the integral. So what you can do is try to manipulate this part into something that's more recognizable in this second part. So what we're going to do is we're going to have the same thing as before for the first part. And we're going to factorize 2 out of this bracket over here. So we get 3x squared minus 5x minus 2. And now we have the exact same thing. But since you factorized 2 out, that means you're going to multiply this whole expression by 2. So when you multiply 6 by 2, you get 12. And the only difference between these two now is this 12 over here. So this is a difference. Okay, but we do know that when we anti-differentiate 12 multiplied by these two brackets over here, that we must end up with this over here. So that's what we're going to write out. We're going to make use of this fact. So I'm just going to take a look at what we got. So we got the integral of 12 2x cubed minus 5x squared minus 4x. I'm just going to stop talking because there's too many terms. Integral with respect to x. is going to equal to, now what was it again? It was 2x cubed minus 5x squared. And the other one was minus 4x. Okay. Oh, where did I go? I'm just going to scroll across a bit. This is a long equation. Okay. To the power of 6 here, and this is to the power of 5. Alright. And of course, when you take the integral, this means that you must have a constant term this side. Okay. But what we want to find is the antiderivative of just this part. This is what we want. What's this 12 doing here? How about we chuck this 12 to the outside and worry about it later? Or even better, how about we try to get rid of the 12? And how do we get rid of it? Well, it's just 12 multiplied by this integral over here. And if you just want to get rid of a multiplication of 12, divide 12 on both sides. And this would give you the integral as stated in the question. And of course the 12, that was the coefficient over here. This one will get knocked out. And since we divided by 12 on the left side, the right side would also have the right side would also be divided by 12, so we're going to get 1 on 12, 2x cubed minus 5x squared minus 4x plus c. Okay, actually, hang on a sec. Is this c and the c up here the same thing? Well, I mean, we did divide the whole thing by 12, so let's take a step back here. First of all, this is actually 1 on 12 multiplied by all of this. So I divided this whole right hand side over here by 12. But this c and this c over here are actually a little bit different. You can say this one over here is c1, constant that we used first of all, and this is still a constant, c1. But what's the difference between a constant that can be any real number and a constant that's divided by 12? Well, there's really no difference. You can say that the 1 on 12 here can be absorbed into this constant. So when you expand this out, you still have 1 on 12 times 2x cubed minus 5x squared minus 4x. But this c1 over here, you don't have to say c1 on 12. You can just say that it's some sort of new constant. You can say it's c2, where of course you can say to yourself that c2 is actually c1 on 12 is equal to c2. But it's just another constant here. It's just any other real number. It's just that it's just the previous constant divided by 12. So if you ever end up having your constant inside your antiderivative changing a little bit, I would recommend using subscripts just to say that they're different constants. But in reality, they're just some sort of arbitrary constant that you can put there, and they can be anything you want. Since we know that with anti-differentiating an expression, and without any boundary conditions or initial conditions, that this constant over here can be anything.